I'm going to talk about is how to use machine learning and data-driven approaches to come up for closures for ocean mesoscale eddies. And so mesoscales are kind of turbulent features in the ocean that have scales of 10 to 100 kilometers or so, and they affect the ocean circulation in terms of steering and mixing and transport of different tracers in the ocean. And so it's been kind of a big challenge in trying to represent that in climate models. And so I'm going to tell you a little bit what we've been trying to do, what we think we've achieved, and most importantly, all the struggles that we still have and all the things we don't understand at all. So it's going to be a little bit of a random walk between what we tried, what we think we know, and what we absolutely do not know, and how to move forward. Okay, so I'm a climate dynamicist, right? So this is who I am. That's what motivates everything in my work. And so here I'm showing projections of dynamic sea level under a given scenario, 1% CO2 forcing. So I'm not using a pointer, by the way, because there is not one that people online can see. So the plot on the left is a multi-model mean. So we take a climate model, we impose a forcing, so 1% CO2 forcing, and then we take another climate model and we impose exactly the same forcing, and then we have a bunch of those climate models, and they all give us a map or projections of what the sea level might look like in the future. And so you see the ensemble mean on the left, so it's basically the average of all those climate models that have felt kind of the same CO2 scenario. So you can see kind of, various features in the Southern Ocean. You see a little bit of a dipole, and we understand those things quite well. So the response of the ocean to a changing in wind and associated transport. The North Atlantic, you can see some kind of red blob over there. And again, it's associated with the ocean circulation and part of the ocean atmosphere feedback that imprint directly onto the ocean. But the plot on the right is the most interesting one, is the ensemble spread. Basically, it tells you where the different climate models diverge. And so again, North Atlantic and Southern Ocean, where you get the biggest signals, is also where you get the largest spread. And quite often, the spread is actually as big as the signal. So even though we know we have a signal, the disagreement in the magnitude of the signal between the different models is actually quite important. And so, of course, you could say, oh, models are bad, but they're pretty amazing because we really understand the physics on the right, but the magnitude of the responses is quite different. And the reason for that is, or at least in part, is that we have, at least for the fluids part, we have equations, and we know those equations, and technically we could solve them if we have, enough computing powers, but we don't. And so for part of the system, what we have to do is we basically need to solve the simulations on the grid, right? And so the size of the grid will limit the kind of processes that you can solve. And so, for example, oh yeah, you can see that. I'll try to do that. Okay, so for example, current climate models have grid of about 50 to 100 kilometers horizontally. So anything that is smaller than that is not going to be resolved. So ocean turbulence, for example, those mesoscale ideas that I mentioned at the beginning are not going to be resolved in a climate model. Clouds, which are a lot more complicated than just solving the basic fluid dynamics because it involves thermodynamics and phase transitions and a bunch of things like this, again, are way too small compared to the gray box size of a climate model. So usually we need to come up with closures or parameterization, which are kind of approximations to these processes. And sometimes for part of those processes, we don't even try to parameterize them. They don't even exist in the climate model. The other source of model error that's going to give you this spread in the projection, some kind of disagreement, is related to the numerics, right? We solve the equations on the grid, and let's assume, you still need to kind of do some approximation of your derivative onto a grid. And the way you do that approximation is also going to give you some errors in different models. Again, when you integrate them, we'll have some errors associated with it. So the uncertainty in projection is to first order due to model error over the next few decades. And two of those sources of model errors, one is numeric, the other ones are, processes that we don't parameterize or parameterize poorly. So the way we've done closures and parameterizations for many years, for decades, actually quite successfully, trying to come up with simple representation of all those processes, clouds, turbulence, mixing, and so on and so forth. So usually the way we've been doing that is trying to come up with a mathematical expression or semi-empirical relationship between the large scale, so between the small scale, and the effect on the large scale. So what we need to do is to come up with a basic equation that's going to tell us how the small scale, as a function of the large scale, will impact the large scale itself. So again, just to give you an idea, we've been talking about steering and mixing earlier. So you get a little bit kind of turbulent features in the ocean as you steer and mix. What they're going to do is they're going to interact with one another, and then they're going to impact the large scale flow. And so we try to come up with simple mathematical models, simple physical model to actually write this down mathematically. So it's been quite successful, but as I showed, still not as successful as we want to be because we still have diverging projections. And so if we look at the current generation of climate models, so the plot on the top is the one I showed you before. That was the previous generation of climate model. And I'm showing you the current generation of climate model, CMIP6. And again, the pattern of projections in sea level is almost identical, right? This kind of dipole in the Southern Ocean that I told you, the red blob in the North Atlantic. But then when you look at the model spread, still hasn't changed. So again, from one generation of climate model to the next, the uncertainty, especially associated with those small scale processes, are a little bit of a struggle. And that's what we're going after. So the main question, and that's why we're here, right? So can we actually develop parameterization that are data driven, but also physics driven, of those kind of small scale processes that seems to be affecting the projections and seem to be affecting our climate models. So the idea is we have a wealth of data sets, right? So in general, it's going to be simulated data sets. So we have a lot of high resolution simulation and we can extract a lot of information from them because they're available, they've been run, and we can run them. So can we extract any information from those simulation and combine them with some physics or some theory and machine learning to actually extract a representation of those small scale processes rather than starting with a basic physical equation, but really trying to ask the question directly from the data. How the small scale are impacting the large scale, and trying to see if we can do better than the traditional closures, and then of course, can we improve climate models. So in the atmosphere, there have been quite a few papers on that actually, so kind of, more than 10 years ago and probably even before that, looking at radiation, convections, and turbulence. So here are just a few examples, but there are many more. In the ocean, we always seem to be a little bit slower, thanks because we have longer time scales, maybe. So we always kind of a little bit slow to pick it up. So there are a few papers, and now it's definitely multiplying, where there's a very nice paper looking at vertical mixing, and our group has been working a lot on lateral turbulent fluxes. That's what I'm going to talk about today. So we're very lucky. We're getting very generous support from Schmidt Futures to actually try to address that. Can we actually look at or derive, if you want, to develop parameterization of small scale processes directly from data that we can implement in existing climate models? So there are a lot of us. So we're climate dynamicists, machine learning experts, and climate model developers to really ask that question on basically, can we actually use data and machine learning to learn subgrid parameterization for the ocean, atmosphere, and sea ice. So today I'm only going to talk about the ocean, which is the work we've been doing directly in the group. And so, as I said, we're going to look at those features, those ocean mesoscale eddies, and you can see it here in this plot. So this is an ocean simulation run at 1/12 of a degree, and you can see this kind of nice Gulf Stream with a little kind of swirls over here, so those kind of coherent eddies. If you run the model at 1/4 of a degree, then it looks kind of more viscous. Then if you go to 1 degree, so that's a grade of 100 kilometer by 100 kilometer, they're pretty much in existence. You basically have a laminar flow. So typical climate models are in this regime over here on the right, right? And what we would love to have is, of course, the physics of this high resolution model, but without the computational cost. And I just want to make one thing clear is that after talking, so Rose talked about, trying to upscale kind of coarse resolution model to get those features. We're not trying to super resolve the flow. We're just trying to capture the physics of those small scale processes on the large scale flow. And so that's kind of a big distinction, is we're going to remain in that coarse resolution world. But we're just trying to basically learn the forcing or the force that I would want to put on the right-hand side of a coarse resolution model to have exactly the same physics, if you want, as a downscale high resolution run. So that's kind of a big distinction between the two work. Okay. So we have a few kind of steps to go through. So the first one is we need to diagnose that kind of missing forcing. What is the effect of turbulence on the large scale flow? And so Rose talked exactly about this kind of idea. You need to find a filter. So I'm actually not going to talk about this because it's kind of warm, but I think she solved it. So we might steal your idea. So what we do is we start with a truth, which is a high resolution simulation, and we need to kind of downscale it. We need to map it onto a coarse resolution grid. So here, if I take the momentum equation, local rate of change of velocity, plus advection, which is the one that causes trouble in general because it's multi-scale, and so you get a lot of scale interacting with one another, equals forcing and dissipation. So we're going to take that equation, we're going to filter it, and we're going to map it onto a coarse resolution grid. And so that's what we do here on the right-hand side. If I filter it, coarse grain it, I end up with this equation, and I get an extra term. And the extra term is basically the difference between the coarse resolution advection and the coarse-grained advection from the high-resolution flow. And so this term that is missing here on the right-hand side is what we're trying to mimic. Can we actually capture this S term, this kind of difference between the nonlinear terms, that is the whole scale interaction that we're missing at coarse resolution? Can we capture that, but only as a function of the resolve scale? So only as a function of the U bar. But if you look at that term over here, right, we care about the U dot grad U. So we don't want U because U is solved on the high resolution grid. So we want to find a term for S that is only going to be dependent on U bar, say. So only on things that are resolved on the coarse resolution grid. Okay, so I'm going to show you two methods. One is basically black box, right? So deep learning, but where we try to bake in some physics. And I think, again, talking after Steve and Rose, I think hopefully you should be convinced. You want to put physics into the black box machine learning. I think that was clear, and hopefully I'm going to make it even clearer. And the second approach is coming up with interpretable equations. And again, actually, some of the work was motivated and definitely inspired by some of Steve's work and the Woody et al. Paper that kind of gave us the idea of doing that for closures directly. So I'm going to show you a couple of examples. Then the third problem is one that we still can't solve because we have no idea what we're doing, is we need to go and implement it back into a model. So I'm going to show you idealized examples with, again, the challenges and what we're facing, but we still never implemented in a real climate model because it's kind of a little bit of a nightmare. And so I think Alistair is going to talk a fair bit about this later on today. Okay, so let's start with, learning subgrid closures from data. So what we're going to do here is we're going to take input, so coarse grain input from different models. And so here it's, I'm showing the stream function, which is basically, a measure of velocity, local velocities. And so quite often we're either going to take the stream function or the velocity on a coarse resolution grid. We're going to use neural nets. Again, this is going to be our first thing. And most importantly, we're going to use convolutional neural networks. So we talked about this earlier already. And what we're going to do is we're going to learn a closure or a parameterization only based on the coarse resolution. To do that, we need to minimize a loss function. So this is this equation over here. So we're looking for a prediction, S hat, which is the representation of the turbulent forcing that we're missing at coarse resolution, given the truth that we diagnose directly from data using the procedure I showed you before. We take a climate model, we coarse grain it, we end up with an S term that we diagnose directly from, from the data, and we learn basically an approximation S hat for that S term over here. So we're going to come up with a prediction that only depends on the coarse resolution field. In our case, it's going to be the velocity. So we've done that with idealized simulations a few years ago, but here I'm showing you when we've done it using the output of a global climate model. It's a couple climate model, and it's run at 1/12 degree resolution, so it's pretty high res by by regular standards. And what we've done is we've used only 4 regions, those 4 over here, so 2 in the Atlantic and 2 in the Pacific, kind of different dynamical regimes. The one in the Atlantic is quite turbulent. In the equator, it's a different type of turbulence, that different type of jets and different dynamics. And we pick also regions where the flow is a lot more quiescent. It's a bit more boring and less turbulent. So we took those 4 regions. And then in this case, rather than learning a mean turbulent forcing, which is what typically has been done, we learn the probability. So rather than say, what is going to be this, S term at a given point, and what's going to be its mean value for given velocity field, we're asking what's going to be its mean value and its standard deviation around it. So we're looking at point-wise probabilities. So we're assuming that the conditional probability is Gaussian, just to make our life a little bit easier. And the reason for that is kind of twofold. First, no matter what we're doing, we're learning an approximation, right? Between a mapping of the velocity onto a turbulent field. So no matter what you do, it's uncertain. So that was one way to actually measure the uncertainty associated with that. And the second one is almost a philosophical one. We're learning a turbulent mapping, between a velocity field and a highly non-linear, expression of that turbulence onto the large scale flow. So having that as something deterministic almost seems wrong. right? So we know for a fact that, again, we're learning a nonlinear mapping. So learning that nonlinear mapping as just a mean rather than a probability seems, again, counterintuitive, or at least to me. So turbulence as kind of a more probabilistic way or stochastic way seems more natural. So rather than learning a mean, yeah, go for it. Oh yeah, please interrupt. It's a lot more fun. That's the good part.
The question would be if you think to include time in this, so an autocorrelation to first order.
Yeah, that's a fantastic question. So here we only did basically concurrent times, but it's something we are definitely exploring. Yeah, it's a great point. So there is memory in the system. So how do you include that? And how do you include non-locality? Yeah, it's a great point. That's one of the challenges, and definitely as one of them. Thanks. Okay, so to do that, we have to change the loss function a little bit. So rather than just showing you the traditional loss I showed you before, it gets a little bit more complicated. It looks like basically a log normal, so kind of fairly simple still. But in the loss now, we need to learn two things. We need to learn the standard deviation at a given grid box, and we also need to learn the mean. So when you manipulate that mathematically, it's still pretty simple and straightforward. And so at the end of the day, given the input, which is going to be the velocity field in a certain place, we end up with 4 outputs. Why 4? First, because I forgot to mention, right? So we're learning a turbulent closure for the velocity. That means we have 2 components, one for u, one for v. So basically 2 components of the velocities. And then the standard deviation associated with each one of the prediction. So in our network, we have 4 channels, and we learn the mean for each component of the forcing and the standard deviation. Then again, we compare it to the true forcing. So I'll give you the good news and then the bad news. So the good news is we trained only on the 1% CO2 experiment in that coupled climate model. So basically the flow only sees, a current or, well, a past climate where CO2 levels were much lower than now. And then we actually check if we generalize to other dynamical regimes, meaning we only train on those 4 regions. And then we look at the R squared, which is basically a measure of the scale everywhere in the ocean. And so when I say lower performance, it's still 50%, right, performance, which is actually quite good in the majority of the ocean. And so again, in most places, we end up with scales or basically R squared that are above 80%. So only training on 4 tiny regions that are, kind of showing you different turbulence regime, we actually can generalize to all other regimes that are quite different. Where we do poorly is where we covered in ice. And that kind of makes sense because it's a completely different flow regime. And actually the turbulence is below the ice, where we never give any of those kind of example. But again, it shows you that you still can generalize, but there are many places where the turbulence might be quite different. Again, when the ocean atmosphere and ice interact with one another, where we do a terrible job. I mean, we need to actually think very carefully what kind of data set we use and how to use them. So again, every time I give you the pros and cons of what we find and what we understand, probably we should do better. The second thing was, let's not retrain the model. Let's see if it's going to work in a climate where the CO2 is much higher than in the training data sets, right? So we want to implement those closures in models that we're going to run in the future. So we need to make sure that they can actually generalize to future climates. Otherwise, well, it's a little bit pointless because my whole motivation was to make, climate projections better. So shockingly and slightly at the same time, it actually does amazingly well. There's almost no deterioration in R squared in a warmer climate offline. The high latitudes, we're actually doing slightly better. And that's why I say sadly is because we melt the ice under CO2. So actually that interaction between 2 different mediums is quite different. So now we're back to something that is a little bit more present day. Okay, so, if I were looking at a time series of those predictions, and, we still do quite a good job, but I just wanted to point out that where we do poorly, it's usually where we get strong extremes. Yes?
Have you tried paleoclimate simulations for training that would have different boundary conditions, essentially?
That's an amazing question. No, we didn't for training, and mostly because I don't know if they are high resolution paleoclimate, but if they are, yeah, that'd be awesome. That's a fantastic question. Yeah, I'd love to see that. Yeah, thanks for that. Great comment. Well, one thing that we can add to the list of something to do. Great, yeah, it'll be actually very interesting to see the different regimes and the different climates. Okay, so here is just a time series of the predictions versus the truth. And so what I wanted to show you, and the dashed lines are confidence interval using the standard deviation. So, I mean, you can say, you can again address this plot in two ways. One, you could say, well, the prediction with its error bar, which are kind of the green line, are always encompassing the truth. That means it was a good idea to actually learn the standard deviation with it, because then that means we're always within it. But the other thing that you could say is that, well, we always struggle getting sharp jumps and extremes. That's something we've been thinking really hard about. Every time that there's a strong change or strong extremes, strong gradients, we're doing very poorly at this. So the question is, should we include more moments? But then that means you usually need more data, and that's a little bit troubling. Or is there memory in the system? And we know there is. So if we were actually, including some of the past events, then could we get those gradients sharper? So again, we haven't tested. So again, I'm telling you all the ideas we have, but things again to think about how we can get that better. Yes.
Sorry, stupid question. It looks like you're actually overshooting the sharpness.
Yeah. So sometimes we overshoot and sometimes we don't. But every time that there is a sharp transition, we just don't get it right. And so here's just one example, but I can take, hundreds of time series and we always get that thing. Either we go way too fast and too strong, or we're just too weak. So we never get it right. Yeah, thanks for that. Yeah, feel free to interrupt. This is fun. This is a fun part of being in person. Alistair.
Well, related, I mean, you assumed it was a Gaussian process. I mean,
yeah.
A statistic, sorry. Have you checked that it is? And is that part of what's going on?
Yeah, excellent point. So we've checked and it's not. So we assume that the conditional probability is Gaussian. And again, the simplicity of it is then you only need to learn two moments, right? So to get the extremes, and we see them, we actually made QQ plots and we check the probabilities, we have tails. And that's usually where we fail. So it's the same representation of those extremes. But the problem is, if you want to learn higher order moments, you need more data because those are the tails. They are the extremes. So you usually don't have enough of them. And how do you learn 4 moments in one go? It makes it trickier. So we have a few ideas that Arthur started, but actually we didn't improve one bit. So we probably need to think a little bit harder on that. But yeah, that's a good point. Anyone else? Yeah, sure. Sorry, I'm letting people. Is that right if we blend the discussion? Yeah, great.
Hi, maybe I missed it, but how do you learn the extremes? Do you learn it from ensembles of those high resolution runs?
Yeah, so what we do is we, at every single grid point, right, we're going to calculate this kind of missing forcing, this S term. Then within the loss function, we're going to assume the missing forcing, this S term, conditional on U, is just a Gaussian PDF. So it's something that looks like this. So when I plug that into my loss function, I end up having to learn the mean and the standard deviation. And that's it. That's the only 2 moments that we learn. Now, in the data itself, right, at every single point, I can plot the probability. And so I can calculate the moments of those probabilities and compare against. So we never calculate the tails themselves, right? We just point-wise learn the truth, but we never learn or train on the extremes. So Annalisa and then Doit.
So you are assuming that the truth is a 1/12 resolution run, which of course is not.
Yes.
And you are also and that's one assumption that at some point we need to make, but there is probably some physics, which is just not well represented there.
Yes.
But the other issue is you are assuming that and maybe I'm wrong here, so this is really where the question is going. You're assuming that the small scales are going to impact the large one. What about the vice versa?
Yeah, so that's an excellent point. So first, yes, those high resolution simulations, we're assuming they're the truth, but they're not. And so, we're actually trying to learn from different type of data sets. Now, are we always assuming that there's going to be a relationship between the subgrid forcing and the large scale, right? That's the assumption we're making. And yes, we're assuming that we're trying to capture this inverse cascade to some extent. Now, there's part of the dissipation that we're not capturing, or we may be capturing, but we're not representing well. So yeah, there's a little bit of both tensions on this. So our strategy right now is to actually look at a wide range of resolution. and see how we can learn and actually trying to understand this kind of, I think this is one of the questions I asked Steve as well, and I think it was also kind of embedded in some of Rose's talk. You have multiple scales that interact depending on the regime that you're in, and can be different Reynolds number, can be different deformation scale. That's something we definitely need to go after, because right now we have one scale, one coarse graining, and one truth. So yeah, something very important to capture.
So sorry, going back to more the question before, I wonder if you could set that up as a spatial problem. So where you could actually leverage the grid points around it rather than going over every point where you can.
Yeah, so that's a great question. So right now, we're learning with CNN, so we're giving a field of view. And so I'm going to show you in a second that I actually use some of that. And can we actually transform the problem where rather than looking at point-wise, Gaussian probability, can we actually try to think about the spatial, autocorrelation, and I think the temporal one as well. So definitely things that to consider for sure. Yeah, thanks for that. Okay, so actually back to the field of view. So we've been using CNN and we're giving a bunch of images to the neural network, right? And we're giving a spatial scale. So now we're trying to ask ourselves, okay, we know turbulence is non-local. So we assume that it would need some information from the points across, right? The question is, how far do you need to go? So how much information do you want? So this is work by Jem, who is a PhD student working with us at NYU with Carlos Fernandez Granda. And so those two lines over here, so this is latitude, sorry, this is R squared, and this is the scale in our learn forcing. And so those lines, there are 2 or 3 up here. They're the same kind of momentum forcing that we learn, giving a given field of view. That's the one that I showed you before. And then he tried to reduce the field of view. So less pixels, if you want. The images become smaller. And then you can see, going from the original one, which was 21 by 21, going down to 15 by 15, and then 9 by 9, there's almost no change in scale. So we didn't need that many points, which is good. I mean, the stencil does not need to be that large. But then you start getting a drop, right? If we go 7 by 7, or 5 by 5, or 3 by 3, your scale drops quite drastically. So it needs some of that kind of spatial, relationship and some of that non-locality. But we didn't need to go that far. We went a little crazy. So it helps us, right? It's helping us because it tells you a little bit of the physics. What do you need? Now, the most shocking one, which I don't understand one bit. So now rather than learning the subgrid momentum forcing for you, we learned it for the temperature. Same lateral flow, same coarse graining and same procedure. And then now, if we use those kind of original 21 by 21 or 15 by 15, scale pretty much the same. If we go a little bit lower, so 9, well, for the momentum forcing, we still gave a really good scale, then we drop quite dramatically. So you don't need the same information for temperature and momentum, which we kind of know physically, that kind of makes sense. I have no idea why the drop is so drastic and why this kind of, scale might be different. And of course, how it changes as a function of latitude, that's another kind of one, because we actually don't give any information about this. So something else to think about, because as a function of latitude, again, we're on a rotating planet, we're on a sphere. So actually latitude is kind of, directly related to the deformation scale, for those of you who are VFD, and that's pretty important and something we probably need to embed somehow in the learning. So again, a lot of open questions with sometimes no answer. Okay, so now that we calculated all things, we need to implement them into a model, right? Because everything was offline, but then at the end of the day, if I want to improve a forward course resolution model, I need to plug everything into an online model. So doing that in the climate model is above my, beyond my pay grade. So we use very idealized model because it's a lot simpler, and we're trying to test things out. So for the stochastic parameterization, what we've done is we took a very simple model. It's what we call a barotropic model. It's basically one layer of fluid. You can think about the flow as being 2D, and it's quite simple, but it can generate jets and things like that. So it's kind of a nice and simple ocean example. And so at every, what we do is we have a forcing on the right-hand side. And the forcing, again, based on the CNN, so we give the velocity field, we pass it through, our network, and we output the mean. But if you remember, we also output the standard deviation. So what we do is we multiply the standard deviation by some white noise, so that we generate. And so at every single grid box, we just, implement this kind of forcing that we sampled from the distribution. And then, of course, because, for every sample that you run, you can actually, you can draw from a different distribution. We run a few members. So here what I'm plotting is global kinetic energy as a function of time. The low resolution is this blue line. So low resolution mean, there's a little bit of turbulence, but a little viscous and a bit boring. And so you can see there is less kinetic energy. The violet curve is the high resolution. So it's 4 times higher horizontal resolution. You can see the amount of kinetic energy goes up, and you can see also the spikes, goes up and down more drastically. So there's more turbulence, but there's also more scale interaction between the small scale and large scale. Now, if we put our low resolution plus CNN that had, some kind of stochastic dynamics in it, those are kind of 3 curves that are almost on top of one another. So we can reproduce the level of kinetic energy and quite other parts of the flow features just from that CNN. And again, the beauty of it is we can run ensembles. So when we want to make prediction, we also get an uncertainty associated with those ones. Okay, so now the problem with all the CNN is it's a lot of fun, and you can, try to interpret what you're getting. And I showed you, changing the field of view and, embedding, learning probabilistically, and it's all great, but you're still stuck because I still don't know what I'm learning, really. I mean, it's awesome, but I'm still a bit confused for why it does what it does. And so what we've been, trying to think is, can we come up with something that is a little bit more natural to us, trained physicists, which is an equation. And as I mentioned, so that was very much inspired by some of Steve's group. Can we learn equation, but not for full dynamical equations, only for the closure part? So there, the problem is you don't quite know the answer, so you're not exactly sure if you learn something physical, so you would need to learn, after the fact. Is the mathematical expression that you learn physical? Does it mean anything? So here we've done the same kind of exercise that I told you before. We take high resolution simulation, we coarse grain it, we, capture this kind of subgrid momentum forcing, and then we pass it through, we basically build a library of function. So I think, again, some of the issues that were mentioned, we have to be careful because we're going to give it derivatives. So we're trying to do it using exactly what the model grid, does. So we are trying to remain faithful to the numerics over which we actually take the data and we learn the data from. So we give the algorithm a bunch of basis functions, velocities, gradient of temperatures, and so on and so forth. So we didn't use Cindy, we used a sparse Bayesian regression, so relevance vector machine. So, but kind of the same idea. You basically, give the library of function to the algorithm, and what it's going to do is going to basically prune through that library of function and output, weight, multiplying those kind of functions. Each one of the weight is going to have a, an uncertainty associated with it, because it's a sparse Bayesian regression. And again, you need to make a few decisions, right? So you need to pick a threshold over which, you assume that this is a good term, and also you put some kind of cutoff, right? You're going to end up with a lot of terms with a lot of weight multiplying a lot of mathematical terms. We decided to cut, at a certain point where the mathematical expression was pretty. So there was a little bit of bias, and also where we're gaining a lot of scale. So it was at 70% with just a few basis function that we could interpret. And so that's what we ended up with. So this kind of beautiful, actually symmetric tensor. So without having, imposed any symmetry, the first few terms could actually be rewritten and combined into a symmetric stress tensor. So there's kind of some, beauty associated with it, and the physics is already captured into it. All the basis function that we wrote could be written as the divergence of a flux, again, because we need to conserve momentum. We can't have a net input or sink of momentum. It can only be redistributed. So that's kind of the beauty out of those methods, is that you learn new equation and you learn new physics. And quite often, actually, you can still capture all the right physics out of it. So we were able to interpret that term, and it actually really, goes back to some old papers of Pope on turbulence theory in 2D. There are a few additional terms because we're learning different type of physics when primitive equation, but really how the stretching and shearing and the rate of change is actually, setting the rate of inverse cascade, if you want, or the rate of energy transfer from small scale to large scale. So that's kind of the beauty of this interpretable aspect, is we learn something that we can go and think about. So then we did the same game, take a simple model and try to plug it, and try to plug what we learned. And so the high resolution is in cyan. The low resolution is this gray line down here. So what we've done is we compared as well against the CNN, in which we basically imposed a constraint. So we use still a CNN, it's not that deep, there's only a few layers, but the last layer, we actually take derivative to build, again, something that conserves momentum. And so at the end of the day, we again, we kind of did the same thing, learn the subgrid forcing, and within the architecture impose some kind of constraint on momentum, and compare that again the equation discovery. So all the curves that I showed you, implies that the CNN does the best. Our equation discovery compared to kind of more traditional closures needed to be tuned down, but it was the same for the CNN. So each one of those schemes, when implemented in the coarse resolution model, improve upon the coarse resolution itself, but all of them need to be tuned, meaning we had a fudge factor in front of it that we had to tune down. Otherwise, either the model was numerically unstable, or in case of the CNN, we called it the washing machine with Tom. The inverse cascade was so good that we ended up with basically just a scale that took over the entire domain. So there was almost no scale for forcing anymore. So it was something quite surprising. So it was overly efficient, in its kind of inverse cascade. Yeah, so we don't know. In terms of extrapolation, it just went too far. There was nothing to stop it anymore because probably never seen anything like that. And you have a feedback, right? Now you're in a forward coarse resolution model, and so you're giving it velocity fields that it might never have seen before, and so the forcing keeps increasing and increasing, and at some point completely dominate. But I still don't understand why it went that far. It seems that dissipation was not as good.
I feel like I keep harping on this, but does that mean that you might have gotten better results by also learning the temporal behavior?
Yeah, so that's a great question. So yeah, that's possible. My guess was that we didn't capture enough of the dissipation of the coarse resolution model. So we went off. And so the dissipation that we have in the coarse resolution model was actually never part of our learning process. So the network, again, had no information about it. And so I think that's something we need to think about as well for our problems, where we need to go and we learn offline, and then we need to go and implement it in the model. But yeah, both are definitely things to think about. Okay, so far I showed you kind of, so I think, yeah, it's my last two slides, so don't worry, since I left everything go through. So everything I showed you is we learn from a model, we implement in another, and we do different tests. And so, it's never good. It's never a good idea. So this is work led by Andrew Ross at NYU. So what we're trying to do is to actually develop standardized benchmarks. So here is taking a very simple 2G model, and of course, it's always nice to have movies. This is the upper ocean potential vorticity in a high resolution run. This is in a low resolution run, that's kinetic energy, and that's entropy. So what he's trying to do is really kind of go after every single step of the problem. Learning the subgrid tendencies with different filters. And again, now we're going to use Ross's idea, and we're going to see how that plays. Do a sensitivity to the machine learning models, different loss functions, different architecture, and then different metrics for offline and online. I think it's very important to have something rigorous if we really want to try to put that into climate models. We can't trust each independent studies finding different things for different reasons. So I think we have to be very consistent in what we're doing. And so here it's done something pretty cool, in my opinion, but I'm biased. So again, this kind of power spectrum, so kinetic energy as a function of wave number. And so what he's done is he said, okay, sparse regression, you need to be sparse, right? And so that was discussed this morning. So you can find a coordinate system, but another option is kind of doing it old school. So we learn from a CNN, but we give different basis functions to the CNN. Then, we learn something directly with those basis functions as input. Then what we can do is we can actually project the output of the CNN onto those basis functions, and you can actually rank them. And then you can decide which one are the most useful. And then you run a symbolic regression, or basically an equation discovery. So you get the best skill out of the CNN, then you project that back onto something much simpler, and you pass it through your kind of, regression algorithm. And so then you can learn an equation that, again, you can go and interpret. And he tried to compare it to our old equation discovery and see if it generalizes. And so again, depending on, which regimes you go, one is better than the other. But doing that within the same framework actually helps us compare different things. Okay, so this is my summary. Hopefully there's more time for questions. So we're still going to need closures and parameterization for subgrid scale process, no matter what we do, also to understand how different scale interact with one another. So we do think, ML can help, improve on domain knowledge, or at least, complement it. So deep learning can have very high skill, and it's generalizable, maybe transferable, but interpretability is hard. But again, we saw kind of different ways where we can go after the interpretability. Equation discovery, I mean, again, I'm a bit biased, I think, because it looks a little bit more like something I understand, but it's kind of, you do it after the fact. You get an equation, does it make sense or not, for the closure problem at least? And it's much more flexible, you know, again, because you can explore different regimes, different scale, is it going to generalize to different climates and so on and so forth. So, you know, in my opinion, you kind of need to find this kind of optimal blend between the physics and machine learning, where you can combine those two approaches together. But there's still plenty of issues, right? So I think we talked about different metrics, boundaries, which I haven't talked about, data quality. So that goes back to using models out truth. They are not, they're still models. So this remains a problem. And implementation, I think Alistair is going to talk a lot about implementation later today. And so hopefully it gives us, you know, a few things to talk about over the next few weeks of things that are possible, but also some of the big challenges that we're facing. And so again, this is part of what we're doing in M-squared lines. We try to kind of, you know, combine those different approaches and different techniques of physics and ML. Thank you.
We have time for a couple, 2 or 3 questions. Okay, let's start with the Zoom ones.
Can you go back to the slide with temperature forcing and momentum forcing? So Raffaele Ferrari is asking if this difference between the two could be related to the fact that temperature forcing is going to depend strongly on vertical fluxes, unlike for momentum fluxes.
Yeah, thanks for that. That's a great point, and it's true that the kind of 3-dimensional aspect of the forcing of temperature or fluxes will definitely play a role here, and so that could be one of the reasons. But I'm still a little bit surprised by the drop in scale by just changing, you know, the input size. This is something that kind of still surprises me a bit. Sorry? But it's, oh yeah, no, fair enough, but it's still a very large drop for scales that again, it's kind of almost independent as a function of latitude. So I get it, but I was still surprised that it was that large that quickly. But yeah. So I think there's one here and then.
Back to your Gaussian fitting problem. Have you tried to make this, instead of assuming Gaussian or moments, making this also empirical? So you can decompose PDFs, making EUFs of PDFs. Then you, instead of having a segregation in the moments, you have the first 2 or 3 modes of the PDF. That's a more efficient way to represent your data.
Yeah, so you can definitely try to build a reduced space and then learn from there. Yeah, so that's a good point. The question is how much of the, you know, non-linearities are we going to miss given the, you know, given the pattern? But that's, yeah, that's definitely a good point. Yeah, thanks for that.
Very nice work, Laura. So at the beginning of this process, there is the step that we need to extract the SGS term, the stress tensor from high resolution data. And I'm wondering to what extent basically the way that the filtering and coarse graining are done would affect the results, the performance of the CNN and also the equation discovery.
Yeah, thanks. Yeah, so as I say, I kind of skip that part because it's my favorite and least favorite kind of warm at the same time. Yeah, so we, you know, I mean, we worked quite hard on this, trying to understand the sensitivity of the way we do the coarse graining. So we went through multiple phases. One where we just did a simple coarse graining, but we're getting a lot of additional kind of noisy term that had nothing to do with the subgrid forcing. So then we went to something where we do a Gaussian filter, then basically coarse grain. So that removed kind of those kind of, you know, kind of ringing effect. But yeah, how you're going to learn that is definitely an issue. How do you do a scale separation in a clean way? And so again, that's why I felt this morning quite inspired by Rose and trying to think about this maybe in a more clever way as she's done. Yeah, it's a great question. And I think there is an influence on it.
Okay, last one.
Super interesting talk. So I'm just curious about like the metrics for probabilistic modeling. like actually, what are the important like quantitative metrics that you think can be used here?
Yeah, that's a great question. So I think there are several parts to the metric question, right? So there's the metric in what you're learning, and I feel learning something probabilistically is the way to go, in my opinion. Again, for some of the reason we mentioned, it's still an approximation, so having some kind of error bar around it, but also it's highly nonlinear. So the mapping is you can't invert it. There's not a unique answer when you invert it. So I feel that's why probabilistically, in my opinion, is kind of the way to go. Now, for different metrics of offline comparison versus online, definitely going to depend on the problem, and so something we can talk more hopefully this week. But thanks for that, Rose. All right.
Okay.
Keaton Burns is asking, it is clear how much stochasticity helps with the model stability, and any idea if it would be stable if you run using just the means from the stochastic closure?
That's a fantastic question. And so if you asked me that question a month and a half ago, I would have said it was crucial. And for our experiment, it was. But then we tried another network, one with mean and standard deviation, and then it wasn't crucial anymore. So yeah, so it's a great question. And I think that's why we went back to trying to do everything within one setup where we can learn and kind of explore each one of those stability issues and so on and so forth. Thank you.